Electricity, wow! It's all around us, isn't it? You can't always see it, but you can see what it does. Think about the lights in your room. Zap! Electricity makes them shine. Think about your television. Click! Electricity brings it to life with shows and cartoons. It's like a super fast invisible helper. This amazing energy powers so many things we use every single day. From the toaster that makes your breakfast crunchy to the computer you might use for homework. It's pretty important stuff, science fans. So, what is this magical-seeming electricity anyway? Well, it's a type of energy. It comes from tiny particles called electrons. These electrons can move. When lots of them move together in the same direction, that's an electric current. Imagine a river, but instead of water, it's full of these zippy little electrons flowing along. That flow is what we call electricity. This movement is key. Without movement, there's no current, and without current, our gadgets stay sleepy. So, getting those electrons moving is the first big step. Now we use electricity for so many things. It can make light, like in a light bulb. It can make heat, like in a stove or a heater. It can make things move, like the motor in a fan or a toy car. It can even carry information, like in your phone or the internet. It's incredibly versatile, which means it can do lots of different jobs. That's why it's become such a huge part of our lives. We've figured out how to harness this electron flow. We've learned to tell it where to go and what to do. And how do we tell electricity where to go? We use circuits. That's what this whole guide is about. Circuits are like special paths designed just for electricity. They make sure the electricity goes from its starting point, does its job, and then comes back. It's a round trip. Learning about circuits helps us understand how all these amazing electrical things work. It's not magic, it's science. And science is all about figuring things out. So let's get ready to figure out circuits together. It's going to be electrifying. Okay, so we know electricity is flowing electrons, but how do we control that flow? We use something called an electrical circuit. Think of a circuit like a racetrack for these electrons. It's a complete closed path that electricity can travel along. If the path isn't complete, the electricity can't flow. It's like a race car needing the whole track to make a lap. No gaps allowed, folks. This complete path is super important for anything electrical to work. Imagine you have a toy train. The train needs a track to run on, right? The track has to be a loop. If there's a break in the track, the train stops. An electrical circuit is just like that train track, but for electricity. The electricity is the train, and it needs a complete path to travel from its starting point, do its work, like lighting a bulb, and then return. This continuous loop is what we call a circuit. It's all about continuous connection. The word circuit even sounds like circle, doesn't it? And that's a great way to remember what it is. It's a circular journey for electricity. The electricity starts at a power source like a battery, then it travels through wires. Along the way it might pass through something that uses its energy, like a light bulb or a motor. After it does its job, it travels back to the power source. This round trip is essential. Without it, nothing happens. No light, no sound, no fun. So, a circuit is more than just wires, it's a system. It's a planned route for electrical energy to do something useful. Whether it's lighting up your Christmas tree or making your remote control work, there's a circuit inside making it all happen. These pathways can be very simple, or they can be incredibly complex, like inside your computer. But the basic idea is always the same: a complete path for electricity to flow and do its work. Understanding this basic idea is the key to understanding all things electrical. Every working electrical circuit, no matter how simple or how complicated, needs three basic types of parts. Think of them as the big three ingredients for making electricity do cool stuff. If you're missing any one of these, your circuit just won't work. It's like trying to bake a cake without flour, or eggs, or an oven. You need all the essential components for the magic to happen. These parts work together in a team. Each one has a very special job to do. First up, you absolutely need a power source. This is where the electricity comes from. It's the part that gives the electrons the push they need to start moving around the circuit. Think of it like the engine in a car, or the person who starts a wave at a stadium. It provides the energy, the oomph, the get up and go for the whole system. Without a power source, your electrons are just sitting around, not flowing, and nothing gets powered. Common power sources include batteries and the outlets in your wall. Next, you need conductors. These are the pathways for the electricity. Most often these are wires. Wires are usually made of metal like copper because metals are great at letting electrons flow through them easily. Conductors are like the roads or pipes that guide the electricity from the power source to the thing using the electricity, and then back again. They form the complete loop or track we talked about earlier. Without good conductors, the electricity can't travel efficiently, or it might not travel at all. And third, you need a load. The load is the actual device or component that uses the electricity to do a job. This is the whole reason we build the circuit in the first place. It could be a light bulb that lights up. It could be a motor that spins. It could be a buzzer that makes a sound or a heater that gets warm. The load converts electrical energy into some other form of energy like light, motion, sound, or heat. It's where the action happens. So power source, conductors, and a load, those are your big three. Let's zoom in on the first of our big three, the power source. This is the heart of the circuit, the part that gets everything started. A power source provides something called voltage. Voltage is like electrical pressure. It's the force that pushes the electrons along the wires. Think of a water pump pushing water through a hose. The higher the pressure from the pump, the more water flows, and the faster it flows. Voltage does a similar job for electrons in a circuit. It's the oomph that gets them moving. One very common power source you know is a battery. Batteries are fantastic. They store chemical energy and can convert it into electrical energy whenever we need it. Inside a battery, chemical reactions happen that cause electrons to build up on one end, called the negative terminal. The other end, the positive terminal, wants those electrons. When you connect a circuit to a battery, you give those electrons a path to flow from the negative to the positive terminal. This flow powers your toys, your flashlight, or your remote control. Another big power source is the electrical outlet in your wall. The electricity from outlets doesn't come from a small chemical reaction like in a battery. It comes from huge power plants. These power plants generate a lot of electrical energy, and it's sent through a massive network of wires to your home. When you plug something in, you're tapping into this big system. The voltage from a wall outlet is much higher than from a typical battery, so it can power bigger things like your refrigerator or a vacuum cleaner. Always be super careful with wall outlets. So whether it's a tiny button battery for a watch or the mighty power grid feeding your house, the job of the power source is the same: to provide the voltage, the electrical push, to make electrons flow. This flow, this current, is what makes our devices work. Different devices need different amounts of voltage and current. A small toy car needs just a little push from a couple of batteries. A big washing machine needs a much stronger push from the wall outlet. Choosing the right power source is crucial for any circuit. Now let's talk about the second member of our big three club conductors, which are usually wires. If the power source is the engine, then the wires are the roads. They are the superhighways for electricity. Wires provide a path for the electrons to travel from the power source, zoom through the load, like a light bulb, and then travel back to the power source, completing the circuit. Without these pathways, the electrons would have nowhere to go, and our circuit would be incomplete. It would be like having a car with no roads to drive on. Most electrical wires are made of metal. Why metal? Because metals like copper and aluminum are excellent conductors of electricity. This means that electrons can move through them very easily. Think of it like a very smooth, wide water slide. The water or electrons just zips right down. Materials that don't let electrons pass through easily are called insulators. Rubber and plastic are good insulators. That's why wires are often covered in a plastic or rubber coating. This coating keeps the electricity safely inside the wire and stops it from going where it shouldn't. Safety first. The thickness and length of a wire can also matter. A thicker wire can generally carry more electricity, just like a wider highway can handle more cars. A very long wire can sometimes offer a bit more resistance to the flow of electricity, meaning it can be a little harder for the electrons to get through. It's like a long, slightly uphill road for our electron cars. So, engineers and electricians have to choose the right kind of wire for the job, considering how much electricity needs to flow and how far it needs to go. So, wires are much more than just bits of metal. They are carefully designed pathways that ensure electricity flows safely and efficiently. They connect all the parts of a circuit together, from the battery that gives the push, to the bulb that lights up, and back again. They are the unsung heroes that make our electrical world possible. Remember, for a circuit to work, these wire pathways must be continuous. No breaks allowed on these electrical superhighways. Keep that current flowing. We've covered the power source that provides the push, and the wires that provide the path. Now for the third crucial part of any circuit, the load. The load is the reason we build the circuit in the first place. It's the component or device that actually uses the electrical energy to do something useful. It takes that flowing electricity and transforms it into a different kind of energy. Think of it as the destination for our electron travelers, where they get to do their important work. What kind of work can a load do? All sorts of things. A very common load is a light bulb. When electricity flows through a tiny wire inside the bulb, called a filament, the filament gets incredibly hot and glows, producing light. So the light bulb converts electrical energy into light energy and heat energy. Another example of a load is a motor, like in an electric fan or a toy car. A motor uses electrical energy to create motion, spinning the fan blades or turning the car's wheels. Electrical energy becomes mechanical energy. Other loads include buzzers or speakers, which convert electrical energy into sound energy. Think of your doorbell or the music coming from your headphones. Those are loads at work. Heating elements like those in a toaster or an electric kettle are also loads. They are designed to get very hot when electricity flows through them, converting electrical energy into heat energy to toast your bread or boil your water. Even your computer or your phone is a very complex load, using electricity to process information and display it on a screen. So, the load is where the magic happens, where electricity gets transformed into something we can see, hear, feel, or use. Every electrical appliance in your home is a load when it's plugged in and turned on. The television, the microwave, the washing machine, they all take electrical energy from the circuit and do a specific job. Without a load, the circuit might still have power and paths, but it wouldn't be doing anything productive. The load gives the circuit its purpose. It's the star of the show. For electricity to do its job, it needs a complete, unbroken path to travel. We call this a closed circuit. Think of it like a drawbridge. When the drawbridge is down, cars can drive across. Similarly, when a circuit is closed, the path is complete, and electrons can flow all the way around from the power source, through the load, and back to the power source. This continuous flow is what makes your flashlight light up, or your toy train chug along its track. It's all about that complete connection. Now, what happens if there's a break in the path? This is called an open circuit. Imagine that drawbridge is now up. The cars can't cross. In an open circuit, the electricity cannot flow because its path is interrupted. If you unscrew a light bulb a little bit, or if a wire comes loose, you've created an open circuit. The electrons stop flowing, and the light bulb goes out. An open circuit means no current, and no current means no work gets done by the load. It's like a roadblock for electricity. This idea of open and closed circuits is super important, and we use it all the time with switches. A switch is simply a device that lets us easily open or close a circuit. When you flip a light switch on your wall to on, you are closing the circuit. You're lowering that drawbridge, allowing electricity to flow to the light. When you flip the switch to off, you are opening the circuit. You're raising the drawbridge, stopping the flow of electricity, and the light turns off. Switches give us control. So, a closed circuit is a happy, working circuit where electrons are flowing freely and doing their job. An open circuit is an interrupted circuit where the flow has stopped. Understanding this difference is fundamental to understanding how all electrical devices are controlled. From the simple button on your flashlight to the complex controls in a spaceship, it all comes down to opening and closing circuits to manage the flow of that amazing stuff we call electricity. It's all about control and pathways. Now that we know about closed circuits, let's explore how we can connect multiple things like light bulbs in a circuit. There are two main ways to do this: series circuits and parallel circuits. They sound a bit fancy, but the idea is pretty straightforward once you see how they work. Imagine you have a few friends and you want to pass a message along. You could have everyone stand in a single line, or you could have multiple lines. That's kind of like series and parallel. In a series circuit, all the components are connected one after another. In a single path, it's like beads on a string. The electricity flows through the first component, then through the second, then the third, and so on, before returning to the power source. There's only one road for the electrons to travel. A classic example is old-fashioned Christmas tree lights. If one bulb in the string burns out, creating an open circuit at that point, the entire string of lights goes out, because the single path for electricity is broken. Annoying, right? Then we have parallel circuits. In a parallel circuit, the electricity has multiple paths it can take. Imagine a river splitting into several smaller streams and then all those streams rejoining later. Each component, like each light bulb, is connected on its own separate branch of the circuit, so the electricity flows from the power source, splits up to go through each bulb simultaneously, and then comes back together to return to the source. This is how most lights in your house are wired. The big difference? If one bulb burns out in a parallel circuit, the other bulbs on their separate branches stay lit. Because each bulb has its own path, a break in one path doesn't stop the electricity from flowing through the other paths. This is super useful. Another thing is that, in a series circuit, adding more bulbs makes each bulb dimmer because they have to share the voltage. In a parallel circuit, each bulb gets the full voltage from the source, so they all shine brightly, as long as the power source can handle it. Science in action. So, we've journeyed through the world of electricity and circuits. We've seen how electricity is moving electrons. We've learned that circuits are like racetracks for this energy, needing a power source, conductors like wires, and a load to do the work. We've uncovered the secrets of open and closed circuits, and how switches give us control. We even explored the two main types of circuits: series with its single path, and parallel with its multiple pathways. That's a lot of cool science. But why is it so awesome to know all this stuff? Well, understanding circuits helps you understand how so much of the world around you works. Think about all the electrical gadgets you use every day. Your phone, your computer, the lights, the TV, the microwave, your toys. They all rely on the principles of electrical circuits. Knowing the basics means you're not just using them. You have a better idea of the science making them go. It's like having a superpower of understanding. Knowing about circuits can also help you be safer around electricity. You'll understand why it's dangerous to stick things into electrical outlets, because you could become part of the circuit. You'll know why you shouldn't use electrical appliances with frayed or damaged wires, because it could cause a short circuit or an open circuit in the wrong place. This knowledge empowers you to make smart choices and stay safe. Safety is always important when we're dealing with the power of electricity, even when it's in a small battery. And who knows, maybe learning about circuits will spark an interest in science or engineering. Maybe you'll want to invent your own amazing gadgets one day. Or perhaps you'll become an electrician, helping to wire up buildings and keep the power flowing. Even if you don't become a scientist, understanding basic circuits can help you troubleshoot simple problems like why a flashlight isn't working. Check the batteries, check if the bulb is screwed in tight. It's practical knowledge that makes you a little more awesome every day. So, keep exploring, keep asking questions, and keep being curious about the amazing world of science.